Good afternoon, this is Schweitzer, and we'll do an introduction into solubility equilibrium. Now, and we'll also talk briefly a little bit more about reaction quotient. Now, in this situation, let's say we have a beaker that contains silver nitrate, AgNO3, and this beaker therefore contains some Ag plus ions and some nitrate ions, Ag plus ions, nitrate ions. They are perfectly soluble, no problem holding a very large concentration of silver nitrate. Another beaker contains NaCl. In this situation, contains Na plus ions, Cl minus ions, Na plus ions, Cl minus ions. We mix them together in a new beaker, and we end up getting a different phenomenon taking place. We end up getting solid AgCl on the bottom. Na plus and O3 minus is going to be floating around. Now, in this situation, we would normally have written this out as this. Goes to NaCl, and this would be in the aqueous state. I'm going to say NaNO3 because that's what it is. And AgCl in the solid. The net ionic equation of this would be Ag plus plus Cl minus yields NaAgCl solid. So we have a few spectators here as well. Now, what's really happening here is that inside this beaker we have the silver ions being dumped in separately, and then the chloride ions are dumped in separately, and of course some of them do dissolve, but eventually we reach our maximum solubility and we just start to precipitate. So the fact that we have AgCl on the floor of the beaker means, one, we are at max solubility. Now, to be at max solubility, generally exclusively we would want to have a solid on the bottom. This max solubility is very often described as molar solubility. Only reason why we call it molar solubility is because we're measuring it in molarity. So when they ask for molar solubility, they mean they want the maximum solubility of this solution when it's maxed out. There is only one way to get more solubility into this particular solution, and that would be to raise temperature. When we start talking about equilibrium, we're referring to the silver ions and the chloride ions exiting the solution, and then there's a re-entry of a solid as well. This two competing processes is where we get our equilibrium occurring. This process does not stop. There are things that are precipitating and there are things that are dissolving, and there are some demonstrations that you could use to show this. For example, if I were just to add more water, well then of course more would dissolve, but then we would regain back to our original value. So either way, we have done some practicing writing out equilibrium expressions that show competing processes. So if I wrote the K value for this, it would be, and we might call SP for solubility, it would be equal to, products, which is a solid, so that would not be included up top here, and two reactants, they are aqueous, so it would be Ag plus concentration times the chloride minus concentration. And at that point, we would get a very legitimate mathematical relationship that shows KSP versus concentrations. When the scientists first developed this, they're kind of like, well, we aren't just creating this for students to study. We're using it, and it's used in industry a lot. And they wanted it to be where as the KSP increased, so did or correlated with the solubility. So they did was they took this reaction and they flipped it. No, very legitimate. They said, okay, we're going to go this way instead. AgCl solid goes to and comes from Ag plus ions and Cl minus ions. Now, the KSP for this reaction is equal to the concentration of Ag plus ions, the concentration of Cl minus ions, and over 1. And this is how they do it. They do not write it in such fashion. They do not use it this way, only because at that point KSP can correlate to solubility. Again, correlate doesn't mean it's the same thing. It's just they kind of walk the same walk. The KSP for silver is 1 for silver chloride. KSP equals 1.8 e to the negative 10th. So this thing is not very soluble. If you come up with another salt, let's say, for example, calcium hydroxide. Calcium hydroxide has a KSP that is 1.7. What is it here? 7. So it's going to be 7 e to the negative 5th. So it's much bigger than that, guys. So you might say that the calcium hydroxide is more soluble. Again, I'm making generalizations. It is generally correct. It is more soluble. All right, so in this case, let's try a couple of questions. In fact, let's use this calcium hydroxide here. And let's say, first of all, I have calcium hydroxide. I want to be able to write out, and you could, I'll post these questions here, and then you can pause it and try it on your own. But what first I want to do is write out the solubility reaction. I want to be able to write out the KSP expression. I want to be able to draw a picture of it. What's it look like? This competition between dissolving and precipitating. And then with the KSP equaling 7 e to the negative 5th, what is the concentration of the calcium 2 plus ions? What's the concentration of the hydroxide ions? And just because it happens to be a base, what is the pH? Okay. In this situation, we have, okay, so you could pause it, try it out. The solubility reaction would be calcium plus 2 OH negatives. The expression, therefore, would be the KSP equals the concentration of the calcium 2 plus, concentration of OH negative squared over 1. Okay, if I am in fact dissolving calcium hydroxide, then I would get solid calcium hydroxide on the bottom eventually, pretty quickly, because it's not that soluble. And I would get calcium 2 plus in solution, but I would get 2 to 1 ratio. The quantities of the calcium hydroxides isn't as important at this point, although we are not very soluble, so you wouldn't want to have a ton of them in there. But the 1 to 2 ratio is important stoichiometrically at this point, this situation. Okay, now, what is the solubility at this point? So one thing you might want to think about at this point is that Q is the reaction quotient. Q, if your initial stoichiometric ratio, and Q is your initial stuff. So before we dump it in, we have an empty beaker that it literally has nothing in it. Empty water, haven't dumped anything in it. So my Q is my current state. Well, the current concentration of calcium is 0. And the current concentration of hydroxide is 0. Oops. All right. And this, of course, gives me a Q value, which equals 0. So this is reflective right there. So therefore, as I dissolve calcium hydroxide in the solution, my concentrations of calciums and my concentration of hydroxides, I'm going to put 2 arrows here because you get 2 of those, will just start raising until Q equals my K value, which happens to be 7 e to the negative 5th. So not a whole lot. This is what my ice table is going to show. Solids will not play a role, but as I dissolve, I'll gain x of this guy, and I'll gain 2x of that one. This is going to be x and 2x. Okay. Now, I'm going to just add those together to get this. So now it becomes a little bit of math. How much do I gain at a 2 to 1 ratio, or 1 to 2 ratio, so that when these things go up, they eventually mathematically equal my K value, which is where I'll eventually get to. So Q will eventually become K, and K could go there. Anyways, so at this point, it becomes algebra. I'm going to sub these values into my expression. Now remember, KSP is because of the same as Q. It really means almost the same thing, Just one's the start and one's the end. So I'm going to take my 7.5 equals, this is my x value, which is the calcium, and then I have this guy here is the hydroxide ion, which is 2x squared. So doing some math, we get this 2x squared is 4x squared times x is 4x cubed equals 7e to the negative fifth. Divide this out, divide the 4 out, so 7/4 is 1.75 e to the negative fifth equals x cubed. Now to get rid of x cubed, you raise it to the 1/3 power. That cancels the cube and also does to both sides, so we don't violate any mathematical rules. X at this point equals 0.026. This is the constant. This represents x. I could take this x and sub it back in here. So the concentration of hydroxides is 0.026. The concentration of the calcium is double that, 0.052 moles per liter. At this point, if you want the pH, okay, I would take, because this represents hydroxides, I go negative log of 0.026, gives me this, because it's going to be hydroxides is your POH. 14 minus that value gives me my pH, and that should be basic and comes up at about 12.4. Check your math. That is your initial start to things that we would want to do with this. Now, one thing you should note is that in this situation, we gave you a K value and we went to essentially a molar solubility. But in the end, we might give you a molar solubility and go back to a K value, and that is possibly likely the next thing that we kind of look to do. Okay, got a little bit of everything here, but solubility is an important aspect in chemistry. Thank you.